Okay, hello everyone. So this week's module is on electric fields, and I'll make three short videos just explaining the most important content from what I've posted on Collage, basically giving you sort of like an overview of the of each of the three sections that I've organized in Collage. But before I get into this week's content, let me just give a brief recap from last module on electrical interactions and Coulomb's law. So this was a problem that some of you asked me about. It was actually one of the exercises in Collage, and I some of you mentioned that you've seen it on the MCAT practice exam. So I thought I would do it here for you, just so I think it gives a good overview of the last chapter. Okay, so you've got this like triangle configuration with three charges. One that is sort of like at the origin, so we can put that here, and that's a positive charge, and we can call that Q1. And so that's at 0, 0. And then another charge that is sort of like on the same axes, but 0.1 meters away from it. So that one is another positive charge, and that we'll call Q2. And that distance is between them is 0.1 meters. And then we've got a third charge that is up a distance of 0.0866, which is a weird number. And it's like midway. So it's like, here, let me draw it here. So it's like up here. Um, so this is plus, and that is a negative charge. So negative Q3. Okay, and this distance here is 0.0, let's just call it 0.08 meters. And then from here to here is 0.05 meters. Okay, so what we want to know is the magnitude and the direction of the electric force acting on Q3. Okay, so we know from what we learned this past week that Coulomb's law defines the force between any two charges. And so to calculate, so let's just draw, first of all, what the forces look like. So this is going to be an attractive force, right, between Q3 and Q1. So that's going to be the force of of charge 1 on charge 3. That's that vector. And then there'll be like a symmetrical vector over here, which will be the force of 2 on 3. Okay, and I hope it's easy to see that because of like symmetry, this is essentially like an equilateral triangle. What I've just drawn there in green. Okay, and then those two vectors are equal but opposite the force vectors. Okay, so Coulomb's law says that the force between any two charges is just the product of the charges divided by their distance, the distance separating them squared. So let's calculate just the absolute value, so we don't have to worry about direction yet, of this force between 1 and 3. So that's just going to be a constant K times the charge of 3 times the charge of 1 divided by the distance that separates them squared. Okay, so we could plug the numbers in, and we would find that that equals around 8 newtons. So let's just put the numbers. So K is about 8.99 times 10 to the power of 9 Newton meters squared over Coulomb squared. And then each of those charges, Q3 and Q1, let's see, Q3 and Q1, they're both 3. So it's just going to be 3 times 10 to the negative 6 coulombs squared. And then we would divide that by the distance separating them, which is, well, we need to calculate that. We need to calculate that. Sorry, I got ahead of myself. So we need to calculate that distance. That's the distance, here, let me draw that, between here and here. right? So that's like the distance between 1 and 3. Okay, so the distance between 1 and 3, we can just calculate using Pythagoras, right? So it's just going to be 0.05 uh, meters squared plus 0.0866 meters squared, and then the square root of that. So if I do that out, I get 0.1 meters. Okay, so that's the distance between Q1 and Q3. It's also the distance between Q2 and Q3. So I can now put that into my equation for r squared. So that's going to be 0.10 meters squared. Okay, so if I multiply that all out and divide, I get just about 8 newtons. Okay, so that is like the vector that is the resultant of this like blue vector that I've drawn here, right? It's that is this. Okay, it's this vector here. It's also this vector because they're the same. Sorry, this is messy. So that's both F the force of charge 1 acting on charge 3, just the absolute value, like we're not talking about direction. And it's also the force of 2 acting on 3, right? Because they're the same.